Hello everyone, thank you for being here and watching this talk. I'm Chen Zhaohui from University of Chinese Academy of Sciences. In this talk, I will present an efficient non-preferred set-channel attack on the CRYSTAL-Dilithium post-quantum signature. I have done this work with co-authors from North Carolina State University. Let's go through this work in 4 sections, including the background and related works, the proposed attack schemes, the real-world experimental results, and conclusions. Digital signature algorithms are widely used to ensure data integrity and non-repetition. The figure below shows a sender sign on a message using his secret key with the signature generation algorithm. Then the recipient can verify the signature with a public key and the message itself. The secret key is credential. If an adversary knows the secret key, he can generate fake signatures on an arbitrary message. Nowadays, we use RSA and ECDSA as international standard. However, these classical algorithms are facing a fatal threat from quantum computing. Dilithium is one of the most promising signature algorithms in the next post-quantum context. Set-channel attacks use the information leakage on the unintended channel. Exactly, we focus on correlation power attack. The underlying CPA works utilizing the relation between secret key and some physical characteristic. A classical CPA includes the several steps, and a succeed attack shows a peak on the correlation plots, and the peak index reveals a time corresponding to the target operation and the key used by the device. This slide shows several remarkable works on secret key recovery attacks. Since the key is constructed as polynomial, most attacks target on schoolbook-based polynomial multiplication or number theoretic transform. Existing template attacks on entity and deep learning-based template attack require the adversary to have access to equivalent devices to build templates. By contrast, CPA do not have this limitation. Other attacks targeting schoolbook or sparse polynomial multiplication are not directly applicable to dilithium because dilithium requires entity-based multiplication. Finalists, etc. provide a profiling technique, but they don't provide an attack implication or any attack results. This work aims to introduce an efficient and destructive CPA. Now we firstly introduce the proposed conservative CPA scheme. The figure on the right hand shows the pointwise multiplication procedure in an entity-based signature generation. The Montgomery modular multiplication output, i.e. the point 2, is an appropriate point. However, the modulus Q is quite large in dilithium. To reduce the table, we give some observations. Firstly, the correct key and its add or subtract SQ all show correlation peaks in modular Q field, and they are equivalent, so the adversary don't have to distinguish them. Secondly, the Hamming weight of a negative number is opposite to the corresponding positive number. Thus, the negative correct key will show a negative peak. With these two observations, we reduce the key guessing table by 32 times. To further accelerate the attack's runtime, we propose a faster two-stage scheme using the 2 points respectively. In stage 1, the adversary executes CPA by targeting the last p bits of point 1. This stage aims to eliminate wrong key guesses by selecting several candidates with high correlations. In stage 2, the adversary first constructs a key guess list using the candidates obtained in stage 1. Then he can execute the CPA by targeting point 2 to recover the complete secret coefficient. Since stage 1 narrows the key guess table, CPA in the stage 2 costs relatively low computational overhead. However, this scheme is not always succeed in the attack, so we need to combine the benefits of the faster scheme and the conservative scheme. The hybrid scheme collocates both the conservative scheme and the faster scheme to combine their benefits. This attack gives priority to the faster scheme if power traces are sufficient. The adversary can judge whether the faster scheme hits or not by comparing the peak value with a threshold. If it hits, the adversary can directly output the correct key. Otherwise, the adversary can use the conservative scheme as a backup. We experiment on an ARM Cortex-M4 core as the figure below. By setting triggers, the oscilloscope captures power traces. Then the adversary can analyze each coefficient in turn. For our experimental device, the max correlation peak value of the correct key is always positive, as shown in Figure A. The negative correct key also have obvious peaks, but the max value of the peaks is negative, as shown in Figure B. In Figure C on the right hand, the correct key and the wrong key guesses can be correctly distinguished with 157 traces. As shown in the table, we test a series of parameters to balance the computational load and the hit rate. Finally, the best parameter size achieves over 7 times acceleration compared with the conservative scheme. As for breaking the dilithium level 2, our hybrid scheme can save more than 3,000 hours compared with the baseline. As a conclusion, we learned to break unprotected implementations of pre-standardized dilithium algorithm, and we test with reference C code on off-the-shelf IoT devices. We can also accelerate the CPA runtime by combining 2 points without false positives. In the future, we will explore on more target devices and also design practical security-enhanced implementations. That's all. Hope you enjoyed this video.